Next is the discussion on simple random sampling without replacement. SRSWOR. SRSWOR means that no unit can occur more than once. Thus, n out of n possible distinct sample size from a population of size n can be collected, which means that the probability of each sample is going to be 1 upon n choose n. However, in practice, we draw a simple random sample by drawing units one by one rather than the sample itself. So what we do is we draw units one by one in such a way that our method of sampling ensures that our samples have a pre-assigned probability of being chosen. So instead of sample, we are using the units. So there are k units. Draw one at a time, so probability of selection of each should be going to be 1 upon k. So what we do is, first a unit is selected at random from a population of n unit. So we select a unit from a population of n units. Then you select another unit from a population of n minus 1 unit, and continue this process till you have drawn a sample of n units. Now we can prove this process gives each sample equal chance of 1 upon n over n of being selected. So this can be proven mathematically, but this is how we actually do it. But the end result is that we get this, and that is the SRSWOR. Now we want to calculate the estimators of. There are two things we would generally like to calculate: estimators of population mean and total under SRSWOR. In survey sampling, often we want to calculate the population mean and the population total, and they are the parameters of interest. Sometimes we also want the ratio of two population totals or mean is of interest. For example, we are calculating total expenditure on food, and then one of the auxiliary variable is the total expenditure of household. Then you get a ratio estimator, which is y upon x or y bar upon x bar. That's a ratio estimator. But let's talking about the population mean. Population mean is y bar, which is, how do we calculate the population mean? Which is just going to be 1 by n sigma I is equal to 1 to n yi's. So that's for the population, but we don't have population, we have samples. So what we get is a y high hat, which is obtained from an estimator y hat, which is calculated by 1 by n I to 1 to n yi's. So this is the estimator and this is the estimated value. Same is with y. If we want to do total y's, then we don't need this because it's just total y. So but we still need I is equal to 1 to n y I, and then we don't have that, so we do y hat, which is going to be n y bar, right? Which is going to be n y bar, which is going to be n over n I is equal to 1 to n yi's. So this the y is equal to multiply by n, you will get the total value. and then the other thing is the ratio estimator, which is the y bar upon x bar. We don't get ratio estimator, we get r hat, which we get as I is equal to 1 to n yi, which is just going to give me all the y bar, which is this thing, which has a 1 upon n here, but 1 upon n gets cancelled here. I is equal to 1 to n xi, that gives you an estimator. So this is the estimator under SRSWOR. This fraction, called n upon n, it is called as the sampling fraction. What we have used here in y hat is this thing, and this thing, it is called as the inflation factor. So the theorem is that the sample mean y bar from a simple random sample is unbiased estimator of population mean y bar. This we had with this we had solved this here, and then the estimator y hat from n y bar is an unbiased estimator of the population total y. So expectation of y bar is y bar. The expectation of y bar is, y bar, all the y bars that you have collected along with their probabilities will give you this, and the expectation of y hat is y. So that is why they are the unbiased estimator. Now there are some other formulas. One is the population variance. Population variance is given by S square, that is going to be 1 upon n minus 1, I is equal to 1 to n yi squares. That is the population variance. This is how you calculate population variance. But what we want to calculate is the variance of yi. This is just a population variance. It should really be yi minus y bar, something like that, but let's just say that this is a population variance. The variance of y bar is expected value of y bar minus y bar square, which is given by S square. So this is the population variance divided by n minus n upon n, which is also S square upon n 1 minus f. So this is how you get the variance of y bar. Then variance of y hat is nothing but variance of n y bar, because that is how you calculate the y hat, and that is a variance of n by var. So then you can just get the n out, and then you just do the variance of y bar, which is just nothing but s square upon n minus n upon n, or you can just remove this whole thing as s square upon n, and you can just do it as 1 minus f. So that becomes the variance of y hat. Then there are certain other things you need to know, which is the standard error of y bar is just going to be square root of this thing, right? So you just take this thing and you square root it, so it's going to become s upon under root n under root 1 minus f. This is the standard error of y bar, and standard error of y hat, so this is sigma y bar and this is sigma y hat. Then you just take this thing and that will become n s upon under root n under root 1 minus f. So that will be the standard error of y hat. When we take a random sample of size n from a infinite population, then the variance of the sample mean is going to be sigma square upon n. This is the variance of the sample mean, right? So that is the sigma square by n, which is just the standard error, variance of the sample mean. Variance of the sample mean when sigma square is the population, so sample mean, the variance is just now, and then if you want to do the standard error, it will become sigma upon under root n. This is the root n sign, which is a very standard definition of standard error, which we always see. So variance of the sample mean is sigma square by n, but that applies when there is a infinite population. When there is a finite population, then you have to apply another factor, which is just a under root 1 minus f is the another. So this is the same thing which we are doing here, which is the population standard deviation, and then you are applying the variance of the sample mean, standard error of y bar, if we are applying this here of 1 by f. So you are applying, so this is what it is. This thing is the multiplication factor you are using because of the finite population. This term is called the finite. So this term 1 minus f is the finite population correction, and you can see that since this is under root 1 minus n upon n, that if n is very small, this value becomes very less and it becomes just 1, and this whole thing becomes n. So the variance of the sample mean just becomes sigma upon under root n. Standard error of estimator of population mean and population total have s in them, right? So standard error or the variance of y bar has s in them, and even the variance of the population total y hat also has capital S in them. So this is the population standard deviation. Now we don't know this, so we have to estimate it from the sample data. And how do we get small s square? We get 1 upon n minus 1, I is equal to 1 n yi minus y bar square. So you estimate it. So then you also can show that for SRSWOR, S square is unbiased for S square. So variance, expected variance or estimated variance of y bar is sigma square y bar that is s square y bar, that is given by s square by n 1 minus f. So variance of y bar, which is this thing, is the same as sigma square y bar, but expectations of it, not that with the um, um expected estimated value of it, that is same as small s square y bar, which is means that you can calculate it from small s square n 1 minus f rather than using the big S. And same thing is with the expected value of variance of the total total population total, which is expected, which is given by this, which is going to be small s square y hat, which is actually y hat, which is going to be n square still there, but we can do small n 1 upon s 1 upon f. So that is how you will calculate the, so this is the expected value of the variance of the sample mean. We have to do the expected value of the variance of the sample mean, because the variance of the sample mean has the population s there, but with population estimate we don't know, so we estimate that we're using the sample here, and we use this theorem to use that. And the same is with the variance. So what is the variance of the sample mean? And this is the variance of the population total, which also can be calculated by s square over here. So this is the simple random sample without replacement.